Hmm?
So you said distribute right here. So I did that right here. Was there like somewhere else I needed to go next from that, or?
Yeah, because remember you have to gather all your y's on one side.
Okay.
And then factor out your y. And then
All right, I was just
divide.
trying to figure out
Yeah,
what's
yeah,
next.
yep. All right. So last time we talked about vertical and horizontal asymptotes. So let's see if we can summarize what we talked about last time, do some examples, and then we'll get into some new stuff. So just to remind, when we had something where the degree on the top was less than the degree on the bottom, we ended up with an end behavior where we still had x's in the denominator. So as x gets really, really big, the fraction gets really, really small, and we had a horizontal asymptote of 0 for that case. When your degree of your top, degree of the numerator, was bigger than the degree of the denominator, we got an end behavior where we still had an x in the numerator. So as x gets really, really big, the fraction gets really, really big, and we don't get a horizontal asymptote. Finally, when the degrees were the same, like this one, we noted that the end behavior just gave us a number, and that number corresponds to what the horizontal asymptote is. So let's see if we can summarize that on the next page. So to recap all of this stuff, if we have a rational function, first part says about vertical asymptotes. Where do we look for vertical asymptotes? What do we look at for vertical asymptotes? You all slept since Monday, clearly. Where do we look? What has to be true? Say again? The denominator is 0, right? So we look at where the denominator is equal to 0 and also not the numerator at the same time, right? So f has vertical asymptotes when the bottom is equal to 0, your denominator is equal to 0, and this again is after you put the fraction or the function in lowest terms. All right. So again, just because the denominator is 0 doesn't guarantee that you get a vertical asymptote. You don't get that guarantee until you make sure everything is in lowest terms. Factor the top, factor the bottom, and cancel out any common factors. Okay. All right. What about horizontal asymptotes? Well, we said that, notice again, if I scroll back up to the previous page, we got a horizontal asymptote here when the degree of the top was less than the degree of the bottom, and the horizontal asymptote was y equals 0. We also got one here where the degrees were the same, and then we just had to look at the ratio of the leading coefficients there. Okay? So summarizing that, so it has a horizontal asymptote of y equals 0 if the degree of the top, which I have denoted by n here, is less than the degree of the bottom, or m. So I'll just write that in words. The degree of the top is less than the degree of the bottom. Okay. And we also get a horizontal asymptote of y equals a sub n over b sub n if the two things are equal, if your n equals m. So it's the degree of the top. I don't know why I wrote numerator on one and bottom on the other. I'll write denominator just to make it consistent. So that's when we get horizontal asymptotes. If you have degree of the top is less, it's 0. If they're the same, you look at the leading coefficients and divide those. Those are the two cases that we have. If the top is bigger, the degree of the top is bigger, then we don't get a horizontal asymptote. We have none. Okay. There's a special case, though. We get a special type of asymptote if we have the degree of the top is exactly 1 bigger than the degree of the bottom. Okay. So to illustrate what I mean by this, what if you had something like f of x equals x cubed minus 2x plus 3 over x squared plus 5? Again, thinking of end behavior, what term matters? What term matters on the top for end behavior? The x cubed, right? What term on bottom matters for end behavior? X squared. So if I look at end behavior again, we have x cubed over x squared. What would that simplify to? Just an x. Now, that tells us we don't have a horizontal asymptote, right? The degree of the top is definitely bigger than the degree of the bottom. But what kind of a function does this look like? It's still a line, right? Asymptotes are lines. The two types of asymptotes that we've talked about so far are vertical ones, horizontal ones, right? Well, this is neither. It's slanted, right? So we talk these when we have the case where the degree of the numerator is exactly 1 bigger than the degree of the denominator, we get what was referred to as a slant asymptote. Another word for that is oblique. And we have a way that we can figure out oblique or slant asymptotes. So let's do that as an example. Okay. So let's look at this function. We have 4x squared minus 5x minus 6 over x minus 1. Just to review, where might this have a vertical asymptote? What makes the denominator 0? 1, right? So, and 1 doesn't make the numerator 0. So 1 is going to be a vertical asymptote here. It's not what the problem's asking for, but I wanted to read that. Looking at the degrees, does this have a horizontal asymptote? What's the degree of the top? 2. Degree of the bottom is 1. So the degree of the top is bigger. Does that have a horizontal asymptote? No. Okay. No horizontal asymptote. But the reason why it has a slant asymptote is that degree on top is exactly 1 bigger than what it is on bottom. That's the cue for oblique or slant. Okay. Here's how you find them. This is why we studied it earlier in the chapter. We're going to do long division. I'm going to take my x minus 1, and I'm going to divide it into my 4x squared minus 5x minus 6. Okay. What do I need to multiply x by to give me 4x squared? 4x. Multiply it through. We'll have 4x squared minus 4x. And then we subtract. What do we get when we subtract? Negative x. What do we need to multiply x by to give us negative x? Negative 1. We'll get negative x plus a 1. When we subtract, we'll get a negative 7. So then remember again how we can rewrite this. We write it as the quotient plus the remainder over what we divided by. Remember doing that a few sections ago? It was on the test, right? Okay. Let's just look at this part right here. The thing I just circled in red. As x gets really, 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 really big, what's going to happen to that fraction? just this fraction. As x gets, if you divide by bigger and bigger and bigger and bigger numbers, what happens to the fraction? It's really, really small, right? So the bigger x gets, the smaller this gets, as it gets essentially 0, right? If this is essentially 0, that's all that's left is that 4x minus 1. So the quotient part here, that's your slant asymptote, okay? So your slant asymptote on this is y equals 4x minus 1. As a matter of fact, we went through all of this work and rewrote it. As soon as you get right here to this step, you're done for slant asymptote. I don't care what the remainder is. Once I get to that step, I'm done. I know what the slant asymptote is. It's the quotient. Okay? So the past here, that work was all unnecessary for finding slant asymptote. As soon as I know this, that's the slant asymptote. Okay? All right. Pardon me. All right, so let's see if we can put all this stuff together to get some graphs. That's the whole point of this. Pardon me. So what we're going to yes. Oh, sure. So the idea on this is to get a whole bunch of information about the graph, about the function, and use it to sketch a pretty darn good graph of what's going on. Okay? These rational functions that we're going to do, we're going to get a pretty accurate graph. Okay? It won't be fantastic, but it'll be pretty accurate. The way that we're going to do that is we're going to figure out where it crosses the x-axis, figure out where it crosses the y-axis, figure out where it has asymptotes, and then basically play connect the dots as we go across. Okay? All right. The first thing you're going to want to do in these problems is factor everything that you can to see what's going on. Okay, do that first. So in this function, we've got x squared minus 5x minus 6 over the x squared minus 3x plus 2. How does the numerator factor? Good. And how does your denominator factor? Good. All right. The reason why I do this is basically 3 reasons. One, remember that before we can find vertical asymptotes, it has to be in lowest terms. That's step 1. Okay? Can I cancel anything? Does anything cancel here? No, so it's in lowest terms, right? That's good. 2, now that it's factored, I can figure out 2 things. Actually, this is 2 and 3. I can figure out 2 things. When is a fraction equal to 0? What has to be true about a fraction if the whole fraction is equal to 0? What do I look at for what's it? The numerator is 0, right? Why do I care about that? That helps me with x-intercepts, right? Where do I look for vertical asymptotes? I look for where the Where do we look for vertical asymptotes? We just said it a little bit ago. Wasn't even on Monday. We did it Monday as well. Where do we look for vertical ones? The denominator equals 0, right? This is why we're going to factor first. Now I know where the whole x-intercepts are and where the vertical asymptotes are. I have both of those pieces of information, right? So what are the x-intercepts for this one? What makes the numerator 0? 6 and negative 1. So the x-intercepts are 6, 0, and negative 1, 0. Let's do part C, and then I'll go back to part B. Where do you see the denominator equal to 0? 2 and 1. So our vertical asymptotes, and remember again, asymptotes are lines. Lines are described with equations. Okay? So I don't want to just write 2 and 1. What do I want to write? X equals 2, x equals 1, right? Remember, asymptotes are lines. Lines are described by equations, not numbers. Okay? This is why we factored first, right? I factor first. I can see if I need to do anything to put it in lowest terms, and I can answer these two questions automatically. Okay? All right. Let's look at part B. How do we find a y-intercept for a function? Plug in 0 for x, right? Now, I can do it in either form. I can put it in over here, but it's probably easier to put it back over in the original form. What do you get on top when you put 0 in for x? -6, and on bottom you get 2. F of 0 is -6 over 2, or -3. So our y-intercept is 0, -3. You would have gotten the same answer had you put it in the factored form. It's just easier to see it in the unfactored form, isn't it? At least I think it's easier to see it. All right. Now, the next two questions, one of these is going to, well, at least one of these is going to be no. Okay? Horizontal asymptote means you approach a horizontal line. Slant asymptote means you approach a slanted line, right? I can't approach a horizontal line and a slanted line at the same time. Okay? Now, it might not have either of them, but at least one of them has to be none, right? You can't have one. Okay? All right. What do I look at for both of these? We look at leading coefficients, right? Or the leading terms, I mean. What's the degree of the top? The degree of the bottom is 2. They're the same, right? So what does that tell you? It's not oblique. Good. Okay. Tells you it's not oblique. How about horizontal? Does it have a horizontal one? Yep. What is the horizontal one? When they're the same, what do you look at? Yeah, the leading coefficients, right? What's the leading coefficient on top is, and on bottom it's 1. So it's 1 over 1, or just a 1, right? Now we have enough information to graph it and get it, like I said, a pretty darn good graph of it. Okay. So let's plot some points here and play connect the dots a little bit. All right. So we said that there was an x-intercept at 6, 0 and -1, 0. We said the y-intercept was at -3. We have, well, this was not great in the middle. We have vertical asymptotes of x equal to 1, x equal to 2. This one's a little bit ugly in the middle. Probably not my best first example, but that's okay. We'll deal with it. And then we have a horizontal asymptote of y equals 0. To start with. All I did here was plot my x-intercepts, plot my y-intercept, and put my asymptotes in. Okay. All right. Now, basically what we've done with the vertical asymptote is slice this up into 3 pieces. I'm going to do something up until I get to this asymptote. I'm going to do something between the asymptotes. And I'm going to do something after the asymptote. Okay? So basically sliced it into 3 pieces. Asymptotes are our guiding lines for what the graph has to look like. Okay? So at each place, I basically only have a couple of choices. I have to get close to this line on this side, to the left side. I have to get close to this line and that line, right? So either I have to go up or I have to go down. Which one is it? Is it up or is it down? Which way does it have to be? I heard it. Somebody said it. It has to be down. Why do you know it has to be down and not up? What do I miss if I go up? The points, right? Those points are on the graph, right? So I know that I have to go close to this line, through that point, and down. That part has to look like that. Have to. Okay? Let's skip the part in between 1 and 2 to start with for the time being, and we'll come back to it. Okay? We'll skip it for the time being. Let's look at the right side. Again, we have two choices because I have to get close to this line and close to that line, right? So it either has to go down or it has to go up. Which one is it? Up, because again, what tells you it has to go up? It has to go through that point, right? Okay. So on the right side, it has to go that way. Does that make sense? Now, I haven't done the middle, but those pieces should make pretty good sense if you follow your lines and go through your points. Okay? All right, the middle piece is a little trickier. I admit it's a little bit trickier. Now, in the middle, I don't have that horizontal asymptote to guide me. I only have the vertical asymptote, right? Because the horizontal asymptote is what happens way out on the ends, right? I don't have a guiding end here in the middle. So in this case, we actually have 4 choices. I could go both ends go up. I could go both ends go down. Or it could crisscross. I could go from up to down, or it could go from top to bottom, or go from bottom to top. I have 4 choices there. I don't have any points to guide me at all. I don't have any horizontal asymptote to tell me that I'm getting close to. Okay? How do I know it's not one of the crisscross ones? How do I know it doesn't do that or do that? If I did this or I did this, what thing do I end up crossing? What's this? That's the x-axis. Is there an x-intercept here? No. We would have found it, right? We already found the x-intercepts, didn't we? So I can't do the crisscross because we don't have an x-intercept there, right? So it either has to go up or it has to go down. The only real way to do that is to try it out and see which it is, okay? Pick something in between 1 and 2. 1.5? Okay, let's go back up to this function. And this is going to help us in the next section, by the way. If I put, let's use right here in my factored form. I don't care about what the value is. All I care about is if it is positive or if it is negative. Okay? If I put 1.5 into this first factor, do I get a positive number or a negative number? Was it? Negative, right? It has to be a negative number, right? Put 1.5 in here, what do you get? Positive or negative? Positive. Over here you get negative, and here you get positive. So you got negative times a positive over negative times a positive. What do you get? Positive, right? So going back up to my graph, and I'll ask the same question. Does it go a U shape upward this way, or does it have to go a U shape downward this way? It has to go up because it's positive, right? I don't know exactly where it is, but I know it has to go a U shape that way. Has to. Doesn't have a choice. Has to be on top. Now, I don't know that it's there. I would need to put a point in there. I didn't actually calculate it, but that's the idea. Okay. This gives us a pretty good graph of what's going on, minus where that might actually be. If I wanted to know where that actually might be, put in 1.5 and use your calculator and figure out what the output is. What questions do you have on that one? All right, let's do the next one. And then I'll let you loose on the last one for practice real quick. What's the first thing I told you to do? Factor. Yeah, that dirty 6-letter F word, right? Factor. Okay. Do I need to do anything to factor the top? No. But if you want to factor the bottom, how does the bottom factor? Okay. That okay? All right. So, first question asks you, what are the x-intercepts? What do you look at for the x-intercepts? What part of that? The numerator, right? When is the numerator 0? So the x-intercept is -2, 0, right? Right? Okay. Y-intercept. How do you find the y-intercept? Put 0 in for x. What do you get out when you plug in 0 for x? -2/3. Good. So our y-intercept will be 0, comma, -2/3. So far, so good? Okay. Vertical asymptote. What do you look at for the vertical asymptote? The denominator is 0. What values make the denominator 0? -3 and +1. So what are your asymptotes? Good. Everybody okay with those 3 parts? This is all familiar things that we've done, right? Find x-intercepts, find y-intercepts. And asymptotes, vertical asymptotes go hand in hand with domain. And we've done domain problems, right? So those all should look familiar. The really new stuff is the horizontal asymptote stuff, right? All right. When we do horizontal asymptotes, for on top and on bottom, what do we look at? Yeah, the degrees first, right? Look at the degrees. What's the degree of the top? 1. Degree of the bottom is 2. What does that tell you about the horizontal asymptote? If the degree of the top is less than the degree of the bottom, your horizontal asymptote is? It's 0, right? Basically what that tells you is, and again, if you think about end behavior, you have x over x squared is 1 over x, right? That's end behavior, isn't it? As x gets really, really big, the fraction gets really, really small. So that tells you that we have y equals 0 for your horizontal asymptote. Okay. What about oblique then? No. Again, the only time for an oblique or a slant asymptote is when what has to be true? The degree of the top has to be exactly 1 bigger than the bottom, right? Exactly 1 bigger. Okay. Otherwise, there isn't 1. All right. Now we're ready to put all this information together. At least I hope so. X-intercept of -2. Y-intercept of -2/3. Vertical asymptote at -3, right? Was -3, yes? Yeah. Okay. I forgot after I scroll down. Vertical asymptote of 1. And a horizontal asymptote at 0. This one, I think the middle part is easier than the outer side, the other sides, because we don't have any points. Okay, so let's do the middle part, and then we'll go on the outsides. Okay. Remember again, in the middle, I've got basically 4 choices here when I'm in between asymptotes. Either they both point up, both point down, or it crisscrosses. Right? What's this one going to do? Are they both going to point up or both point down? No, it's going to miss those points, isn't it? So it's going to have to go from upper left to lower right, that direction. It's going to have to do that. It doesn't have a choice. So we've got to go down this way and over and down. We don't have a choice in the matter. Again, asymptotes, you have to get close to the asymptote, right? And I have to go through those 2 points. It's got to go down this way. It can't turn around and go back up because we would have saw an x-intercept there, right? So it can't go down and up or up and down because we would have saw asymptote. So it has to do that crisscross. All right, now we got to figure out, pardon me. It either, on the outsides, it either goes that way or it goes that way, right? We got to figure out which way it is. Let's do the same thing we did before. Our function was, let me write it back down. We factored it. X plus 2 over x plus 3 times x minus 1. Right? Okay. I want to figure out what happens over on this side, right? That's where we're looking. Put in a number that's less than negative 3. What's less than negative 3? Negative 4. If you put in negative 4, is the top positive or negative? It's negative on top. Put it into the x plus 3 factor. Is it positive or negative? Negative. Put it into the x minus 1 factor. Is it positive or negative? It should be negative again, right? So they're all negative. So what does that tell you? The whole thing is negative, right? Okay. So let me ask you again. Is it going to be drawn up here or down here? Down, because it's negative, right? So it's not this one. So again, if I draw it, I want to get close to each of the asymptotes. Not looking for perfection, just trying to get the idea of what it looks like. All right, how about on the other side? Pick something bigger than 1. 2. On top, when you plug in 2, you get positive. On bottom, you get positive times positive. And so the whole thing is positive. Okay. So am I going to draw it up at the top or on the bottom? On the top. It has to go that way. Is that okay? All right. Work on the next one for a minute. We'll chat about it, and I'll leave the. We'll do the last one just for one part of the last one, and I'll leave the rest for practice. But work on the next one for a minute, and then we'll chat about it. Notice on top, the only thing you can factor out is a 2, right? When you factor the 2 out of the top, you should get a 2x minus 5. So it's already in lowest term, so we don't need to worry about canceling anything. What did you find for your x-intercept? 5 over 2, right? We would set that 2x minus 5 equal to 0, right? So we would have 5 halves, comma 0 for that one. What'd you get for your y-intercept? 0, negative 2? Yep. So again, we put in our 0 for x, and we get a negative 2. So we get 0, negative 2. Exactly. Are we okay with those two? No, maybe. Okay. How about vertical? What do you look at for vertical? Denominator. When's your denominator equal to 0 here? Negative 5 halves. So the vertical asymptote would be x equals negative 5 halves. And again, you can always just set it equal to 0, right? If you need to. And it would subtract your 5 and then divide by 2. You can always do it that way. Okay. I already wrote there wasn't an oblique asymptote because the degree of the top and bottom are both what in this case? 1. So what's your horizontal, since they're the same, what's your horizontal asymptote in this case? 0. If they're the same, what do we look at when they're the same? The coefficients, right? So it'll be 2. All right. So we're ready to put all this stuff on the graph? So we had a vertical asymptote at -5/2, a y-intercept at -2, an x-intercept at +5/2, and a horizontal asymptote at 2. So now we've basically just got it divided into 2 pieces now, right? So on the left-hand side, it either has to be up at the top, above that above that horizontal asymptote, or at the bottom, below it, right? Which is it going to be? Is it going to go up as you go to the right, or down as you go to the right?
Up.
Why does it have to go up?
Because whenever you plug in -4 on any of those numbers, it'll always be negative. On the top and the bottom. So positive.
Okay, good. What would you cross if it went down? The x-axis. Did we find any x-intercepts over there? No. So it has to be on the top, right? If it went down, it would have crossed the x-axis, and we would have found the x-intercept already. So it has to go that way. What about the other one? Is it on the top or on the bottom? Is it? Yeah, it has to be on the bottom. What tells you that it has to be on the bottom? The points. You have to go through the points. Yeah. So it has to go that way. Yep. Has to do that. What questions do you have? All right. I just want to do one part of this last one. I'll leave the rest for practice, and then we'll talk a little bit about new stuff. What's the degree of the top? 2. What's the degree of the bottom? 1. So that tells you have what kind of asymptote? Slant, right? The oblique or slant, right? So again, to do your oblique or slant asymptote, we have to do, there's no other way to do it besides long division. Don't try to do a shortcut, okay? You have to use long division, okay? We multiply, what do we need to multiply 2x by to give you 4x squared? 2x. Multiply that through, you get 4x squared plus 4x, and we subtract.
No,
-5x, good. And then what do you multiply 2x by to give you -5x? -5/2. And at this point, we can stop. We don't have to go through and figure out what the remainder is. The quotient is your slant asymptote. Okay? So we can just write y equals 2x minus 5/2. So once you find the quotient, that is your slant asymptote. You don't have to do anything else. Okay? You don't have to go through and do the subtraction or anything else at that point. I'll leave the graph for you for practice, but I do want to talk about a couple of things today, and then we'll finish this section, this handout up on Friday. All right, so the first part of this handout gives a couple of definitions, and then we'll talk about a theorem here. And then we'll do some other solving. We'll do some solving on Friday. So the first things that we talk about are what we mean by a continuous function and what do we mean by a smooth function. Both of these have to do with the graph of the function. Continuous just means that when you draw the graph of the function, so when we draw the graph of y equals f of x, we can do so without lifting our pencil. Okay? That's roughly speaking what we mean by continuous. So those rational functions, those last ones we just graphed, are those continuous functions everywhere? No, because we had to lift up our pencil to go from one side of an asymptote, a vertical asymptote, to another, right? So those are not continuous. When we graphed, pardon me, when we did the graphs of polynomials before, are those continuous when we did polynomials? Those graphs like we did on the last test? Can you go from left to right? Did we have to lift up our pencil to go from left to right? No. So those are kind of polynomials are continuous. Okay. So that's what we mean by continuous. If we draw it out, we can do it without lifting our pencil. Okay? Or pen or crayon or whatever you're drawing with. Okay. Oops. So what we mean by smooth is we mean no sharp corners. So if the graph of y equals f of x has no holes, so it has to be continuous, and has no sharp corners. Oops. Can you think of a function that when you graph it has a sharp corner? Can you think of one of our catalog functions? Absolute value has a sharp corner at 0, right? So that's an example of a function that's not smooth at 0. Okay. So continuous has to do with connected, no holes. Smooth has to do with no sharp corners. Okay. Now what we're really going to be interested in for this particular theorem that we're talking about is the idea of a continuous function. Right? So what we refer to this as the intermediate value theorem. It's actually a special case of the intermediate value theorem. And the idea here is it helps us figure out a place where a function might cross the x-axis, might help us find where a 0 is. Okay? So what it says is that if we have a function and f of a and f of b have opposite signs, so maybe my a is over here, my b is over here. If f of a and f of b have opposite signs, that means I have 1 point below the x-axis and 1 point above the x-axis. If it's going to be continuous and I'm going to connect dot at A to dot at B, what am I going to have to do to some point in the middle? If I get from here to here, what am I going to have to do? Relative to the x-axis, what am I going to have to do? Cross it, right? Somewhere I've got to cross it, right? Does it tell me where necessarily? It just says that I have to, okay? So what this says is that somewhere at some value, we'll call it C, between A and B, we must have f of C has to be 0. So somewhere in between, we have to cross the x-axis. That is all that says. How do we use that? Well, let's look at this example, and then we'll do another example on Friday, and then we'll get into how we use this to help us solve inequalities. We have the function here, f of x equals x to the 4th minus 2x cubed plus 10x minus 25. It asks us to show that it has a 0 somewhere between 2 and 3. That's what that says in the interval from 2 to 3. It just says somewhere between 2 and 3. Okay. This is a polynomial. Polynomials are very, very nice functions, right? They're continuous, correct? So what we need to do in this case is we plug in 2 and we plug in 3. Plug in the endpoints. When we plug in 2, we have 2 to the 4th minus 2 times 2 cubed plus 10 times 2 minus 25. I think you get negative 5 if I did that correctly in my head as I went across. You get what? I don't think it's 3. Because this is 16 minus 16, which gives me 0. And I get... Okay. Now when we could put in 3, What is that? Somebody's got an alarm going off. All right. What do we get here when we put in 3? We get 81 minus 54 is 27 plus 30 is 57 minus 25. 57 minus 25 is 32. Right? Assuming I did that right. What's the important part of this? Do I care what the values are? No. I care what the signs are. One is positive and one is negative. They have opposite signs, right? Okay, so this tells me, since these signs are opposite, there must be a place, and it'll be done here in just a sec, must be a place between 2 and 3 so that f of c equals 0. There has to be a place in between where it crosses the x-axis. Okay. That's how the intermediate value theorem works for us for finding zeros. So we'll do another example of this next time at the beginning in class on Friday. And then we'll also talk about how we use the intermediate value theorem to help us solve inequalities. Have a good one. We will see you on Friday, if not before.